Hey everyone, this video is part 2 of the two-part lesson on polarity. If you haven't watched the video on bond polarity, stop now and go back and watch that video first before we dive into this one. In that last video, we talked about what makes a bond polar, specifically that a polar bond is when two atoms share their electrons unevenly due to their difference in electronegativity. But we now need to be able to expand on that and look at how the bonds in molecules are arranged in three-dimensional space and what effect that has on a molecule and its polarity. So, in order for a molecule to be polar, okay, and again, that means it has a slightly negative side and a slightly positive side. So in order for that entire molecule to be polar, it has to have polar bonds. Okay? It can't be polar if it doesn't have those polar bonds that we talked about in that first video. Okay? If those electrons aren't being shared unevenly, then we're not going to have any unevenness in the entire molecule. And that's what polarity is all about, is being uneven. So we have to have unevenness in the bonds before that can be expanded into the molecule. Okay? The other thing that makes a molecule polar is if those polar bonds are not evenly surrounding the central atom. So we talked about Lewis structures and molecules that have one central atom, and that's what we're continuing to talk about here. If those pendant atoms that are bonded to the central atom are not perfectly evenly surrounding the central atom, and we're talking about 3D, 3 dimensions here, then that molecule is going to likely be polar. When we have those two things together, so polar bonds not evenly spread around a central atom in a molecule, that results in one end of the molecule being slightly positive and one end of the molecule being slightly negative. Okay, we can say like also known as having those poles, right? We talked about north and south poles in the last video. We have a positive pole and a negative pole of our molecule. Okay, so if we look at the examples on the right, this one on the top is water, okay, H2O. Because the oxygen has these two lone pairs up here that aren't really depicted here because they're not atoms that we draw in the molecule. Those two lone pairs push on those hydrogen atoms. And so when those two lone pairs push on the hydrogen atoms, this makes this molecule a bent shape. Okay? So since those hydrogens are unevenly surrounding the oxygen, they're clearly pushed to one side. That makes this molecule asymmetrical, and therefore water we always consider to be polar. Okay, you guys actually in biology should have talked about water being polar for almost a whole unit. If we look at the CF4 molecule at the bottom, okay, the central atom is carbon, and we can see that the fluorines are spread evenly. This is a tetrahedral shape. Tetrahedral. Okay, so those fluorines are evenly spread out in 3 dimensions around the carbon. Because we have that 3D symmetry here, this molecule of carbon tetrafluoride would be considered nonpolar. Okay, so we need to know that even, okay, or symmetrical is equal to nonpolar. Okay, and then the opposite, right? So asymmetrical, should be a Y in that word. There we go. Asymmetrical or uneven is going to mean polar. Okay, so let's look at some shortcuts that we can use to figure out if something is polar or nonpolar. Okay, so it's really all about that symmetry, like I said, but it's symmetry in 3 dimensions, not in 2D. So it's not just based on how your Lewis structure is drawn, it's based on how it looks when we picture that shape in 3 dimensions. Okay, so some shortcuts for you. When atoms are bonded to the central atom that aren't evenly spread out, okay, that's going to make a molecule polar. So again, this is a pattern, not necessarily a hard and fast rule, but we can think about some of those shapes from our VSEPR chart that tend to be polar. Okay, shapes that tend to be polar are going to be bent, right? Just like that water, and also our trigonal pyramidal. Ooh, is really going to pyramidal. Really test my spelling skills. Okay, we also can maybe think about like linear with just 2 atoms. So just like one single bond being a whole molecule. Okay, so bent molecules, trigonal pyramidal molecules, they have those lone pairs that push those atoms to one side of the central atom, and so that those tend to be more polar. Okay, the other shortcut is if I have more than one type of element bonded to the central atom, it's always going to be polar. Okay, that's always going to lead to some unevenness. So you can see this example CH2Cl2 in the Lewis structure. Yeah, that looks pretty symmetrical, right? But if I think about it in 3 dimensions, like we see here, we can see that those chlorines are on one side, the hydrogens are on the other side. That is not even and identical in that 3-dimensional space. And so if I have more than one type of element around that central atom, always going to be polar. Okay, so some shortcuts are bent, trigonal, pyramidal, and linear with just 2 atoms are going to tend to be polar. And when I have more than one type of element bonded to a particular central atom, then that's going to also be polar. So what I'm generally going to ask you to do is and even on, an exam or moving forward in your sciences, you might just be given a formula and have to determine whether that element is polar or nonpolar. In order to do that, you have to go through some beginning steps. Okay, so step 1 is going to be to draw the Lewis structure. I'm not going to go through all of the individual steps of drawing a Lewis structure on this video. You can check out the video on drawing Lewis structures for that. I'm just going to go ahead and draw it really quick. So this example we're working through is CBr4. I'm going to do it in a different color just for fun. So carbon's going to be the central atom. We have 4 bromines bonded around it. Okay, and then I'm going to have my lone pairs around the bromines. And you're going to trust me that that's the correct Lewis structure for carbon tetrabromide. So step 1, check. Step 2, we need to look at our VSEPR chart that you should have written down or somewhere in your chemistry things. In that VSEPR chart, you're going to look for 4 things bonded to the central atom, right? I have 1, 2, 3, 4 bromines here. I do not have any lone pairs. And so my chart should tell me that this is a tetrahedral. Check for step 2. Step 3, we're determining bond polarity. This should be a quick one. Okay, determining bond polarity, all I mean by that is to make sure that the bonds are in fact polar by looking at whether they're between different types of atoms. 99% of the time, they are going to be between different types of atoms. So yes, these are in fact polar bonds. Okay. Now we're going to look at the distribution of those bonds around the central atom, and I'm going to think about my shortcuts. Okay. A tetrahedral shape is not one of those polar shapes that I listed, right? It's not bent, it's not trigonal pyramidal. And in this tetrahedral, I only have bromine around that central atom. Okay, I only have bromine around the central atom, so it's not meeting the criteria for that second shortcut that I talked about. And if I look at my Lewis structure here, it does look pretty even. So that means that this molecule overall is going to be non-polar. Okay, so again, your steps, you draw your Lewis structure, use that Lewis structure to determine the shape, make sure we have different elements going on, or you can even maybe do that in a different, maybe after step 1 or as step 1, doesn't matter. But number 4 is where we're determining polarity, right? That's where we're looking at that evenness. If it's even and not meeting those 2 shortcut criteria, then it's going to be nonpolar. If it's uneven and meets those 2 shortcut criteria that were on the previous slide, then it would be polar. All right, so I'm going to work through a couple more examples and show you the molecules. So I'm going to go to the next screen that has my examples on it. If you want to pause and try yourself, I highly recommend. If not, feel free to just watch me work through it just like this one, but maybe a little bit quicker. Okay, NH3 is this example. Okay, I'm going to draw my Lewis structure really quick. It's definitely probably going to take you a little bit longer to draw your Lewis structure as you're practicing. Okay, but that's what it looks like. It has NH3 is going to have nitrogen in the center, 3 hydrogens, and then we have an extra pair of electrons to sit on that nitrogen atom. That extra pair of electrons is actually going to make this a trigonal pyramidal. That word is very hard to spell, and I probably spelled it wrong. Apologies for people who like spelling. I'm not good at it. So that's trigonal pyramidal, right? If I were to draw it kind of in 3D, it's going to look like this. Maybe this one's further back. Looks like a little pyramid, right? With the nitrogen on the top. This is one of those shapes that we talked about in our shortcut, right? This shape, I told you, tends to be polar. So this is where we look at step 3 and say, okay, are the bonds polar? If those bonds are polar, then we are good to go to say that this molecule is polar. Nitrogen and hydrogen are definitely not the same electronegativity. They live very far away from each other on the periodic table, and they're not going to share those electrons evenly. Since this is then one of those polar shapes, this molecule is polar, right? We can see those hydrogens, if these are our hydrogens down here, they're all pushed to one side in 3 dimensions. Being pushed to one side means they're uneven, and it means this molecule is polar. Okay, so here are some more examples I'm going to go through real quick. Again, this might be a good time to pause your screen. I'm just going to go ahead and write the answers up here really quick so you can do some more practice. Okay, carbon dioxide, linear, no lone pairs on that central atom to push those oxygens around. They get to spread out perfectly evenly. This does have polar bonds, but since those polar bonds are evenly spread in 3 dimensions around the carbon, we say that that is a nonpolar molecule. Okay, boron trifluoride. My Lewis structure drawn here. It is a trigonal planar molecule. Okay, boron is an exception to our octet rule, so there's no double bond here. It should look just like this. Okay, trigonal planar is not one of those polar shapes that I gave you, so even though this does have polar bonds, those polar bonds are evenly spread, so this molecule is non-polar. Okay, the last thing we need to talk about is why this matters. We actually deal with polarity every single day in our lives. Whether a substance is polar or nonpolar determines what it will mix with. So polar things will only dissolve or mix with other polar things, and nonpolar will only mix with other nonpolar things. So we remember this rule by the phrase like dissolves like. So for example, oil will not dissolve in water. Okay, you can see in my picture of water and oil here, water is very polar. It's got this negative and positive side. Okay, whereas this is oil here, and this is not very polar, right? It looks pretty even. there's nothing there for the water to stick to. Okay, but this is why soap works. So soap has a polar end and a non-polar end. It's got a little bit of both. The non-polar end, sometimes we can call hydrophobic. Okay, whereas the polar end we can call hydrophilic. These are terms you may have heard in biology. Hydrophobic meaning water fearing, right? Hydrophilic meaning water loving. Those are kind of other words for nonpolar and polar, respectively. So since soap has both parts, it can mix with anything. Okay? In fact, the nonpolar end of the soap will stick to and surround any nonpolar object, okay, or substance, I should say, like oil or grease. When they do that, the polar end sticks out, right? And it's all that's then surrounding that polar or that non-polar grease particle are the polar ends of the soap. Well, now these polar ends of the soap are very happy to interact with water. Like dissolves like. So water will definitely dissolve the polar ends of that soap molecule. So what that does is the duality of soap, the polar and nonpolar qualities, shield the grease and essentially disguise it as polar to then mix with water and go down the drain. Okay, this is very relevant to what we do every day, right? We wash our hands or we, wash our dishes, whatever it is. And many germs and viruses have nonpolar and polar parts that soap will disrupt. And so when those germs or even just dirt and grease become in contact with soap, they can get dissolved and be washed off and go down the drain and be ridded from ourselves or our dishes, whatever it is. Okay, so this is why it's important to wash your hands with soap and water to kill all those germs and potential viruses and yucky stuff that could be on your hands.